This video was produced by
folks, it's a little after 10:30, so I thought maybe we'd go ahead and get started. If you want to take a seat. I believe we're the only session taking place right now, so we're the only game in town, so hopefully this will entertain you here up until lunchtime. My name is Jay Titlow. I'm a meteorologist with Weatherflow, and we have three great panelists here. We're going to talk about wind resource assessment, and I'm relatively new to the wind energy game. I'm a meteorologist, and I've always been stunned that wind resource assessment is not the only aspect of developing a wind farm. You know, to me, it's everything. Of course, I'm biased, and you'll see that as I continue to talk about the importance of wind. But I think wind resource assessment is, Katie Chapman in the last session basically was talking about there was a 10 to 15% underperformance that she was talking about, and she didn't mention wind resource assessment, but I wanted to ask her whether how much was applicable to the wind resource assessment, whether that's actually, you know, that we're seeing those the wind resource assessments being accurate or not. One of the things that I'm quite curious about is the reliability of wind, and I don't know if that makes it into wind resource assessments. Maybe you can comment on that. But a sea breeze is a very constant wind, and it's very dependable, and it's a clean, usable wind. Winds associated with a cold front, maybe gusty, may shut off with precipitation, things like that. So I'm also curious about wind, whether you folks, we can have a little exchange of conversation about the quality of wind when we talk about wind resource assessment too, as opposed to just an annual average or something like that. So that being said, we have three speakers. We're going to start out with Bill Rogers, and Bill is going to talk to us, give us a little bit of a history of wind resource assessment, and then we'll follow with Lynn Sparling. And then we'll end up with Fred here before lunch, and Fred will hopefully keep us captivated so that we won't, our growling stomachs won't on the edge of our seats. So without any further ado, I'll turn the mic over to Bill.
Thank you. Thank you, Jay. My name is Bill Rogers. I'm with Solaya Energy, and I'm really happy to be here. I'm really happy to be here for a couple of reasons. First of all, JMU is dear to my heart. We've actually hired our chief wind analyst, graduated from JMU, and by the way, applications will be available at my desk before you leave. But anyway, yes, wind resource assessment is a very, very crucial part to developing any wind project. Basically, no wind, no project, and you have to really assess and prove that you do have consistent wind. Back in the late 70s, the original modern wind farms were the developers and researchers in Denmark were the pioneers of the first real assessment tools of wind, and that has evolved. Anyway, the long and short of it is, we start out with wind resource maps, and maps can be government edition, they can be private edition, and what that does is that allows you to hunt areas that potentially have good wind. And after you do that, you move on to actually picking a site and taking measurements. Now, measurements can be done, for the most part, by meteorological towers. These generally range 60 meters high. They have anemometers, wind vanes, sometimes temperature and pressure units, relative humidity units. Data from these towers are collected for at least a year, generally 3 years. This data is then scrubbed, and basically what that means is the anomalies are taken out, the missing data is interpolated through, and with that, once you have that data, you then take that data and you reference it across the Met towers that you do have, and then you reference it to long-term data collection, which could be from airports, it could be from municipal facilities, it could be from other government facilities. What that does, basically, it gives you a long-term projection of what the future energy could be, or what the energy output could be from a wind farm. We've been very, very fortunate to partner with JMU and Dominion on a SODAR project here, actually in Virginia, where we have 3 Met towers, and we've used a SODAR unit to basically take the anomalies out of a very complex terrain by moving the SODAR unit, first of all calibrating it next to a Met tower, and then moving the SODAR unit progressively along this complex ridge. I think it's been a good opportunity for both JMU and a good opportunity for this particular project. After you get the data that you feel is, and that's measured in meters per second, after you get the data, then you get into the calculation stage. And first of all, you correlate between your Met towers. You could have as many as 5 or 6 Met towers in a large site. And then you correlate with the long-term weather stations. Then you evaluate shear. Basically, Met towers, as I mentioned, were 60 meters high. A lot of the hub heights for wind farms could be 80 or 100 meters. So you need to basically extrapolate and predict what it's going to be up, what the wind shear is going to be at 80 to 100 meters. Then you do wind flow modeling, and basically you're extrapolating the wind speeds across the site. And as I mentioned, you know, that's called a roughness factor. And that can be, depending upon the terrain, particularly in Virginia, in a mountainous area or on ridges, it can be a very, very difficult thing. And there's plenty of software out there today. There's companies that do this, and it can be very complex. After that, once you realize, you know, that you have this meters per second or this data, then you can get into the energy production by using the wind turbine manufacturer's power curves. And after, basically you can calculate the amount of energy that's going to be output in basically the financiers will know exactly what they're getting into as far as funding a project. Another thing too is that application, after you do get the energy production, you need to take into consideration wind turbine wake loss, wind turbine availability, but that hasn't been an issue in the past couple of years. Electrical losses, blade degradation from ice, dirt, insects, high and low temperature shutdown, high wind speed shutdown, curtailments due to grid losses. Anyway, the bottom line is it's a very, very complex process that is absolutely necessary to determine if a project is financially feasible. There are many, many software applications out there today that take a lot of this information into consideration. And just moving on here. I guess that's what I have, but the bottom line is the wind resource assessment is absolutely critical to developing a wind farm. Thank you.
Thanks, Bill. I think what we'll do is we'll hold questions to the end, and then we'll have a chance to fire away at all three of these guys. The next up will be Lynn Sparling from the University of Maryland, Baltimore County. Lynn will be telling us a little bit more about resource assessment, some of the pros and cons and some of the pitfalls, and she's been working diligently on her presentation. So, one thing I want to mention while she's loading up her presentation is from developers and folks who basically don't come from the meteorology side, one of the things I'd be curious to learn about a little bit more is kind of backing out when I was mentioning previously about production not necessarily coming up to equaling what was expected from resource assessment. And for example, one of the things, I'll just give you a couple quick meteorological anecdotes. We gave our data from our network to the Volvo racers, the sailboat folks coming up to Chesapeake Bay. And we were very excited about them using our data. And we thought, boy, this is going to help one of these racers win the race. And so I was very anxious to hear how the teams did when they used our data. And they said, well, I hope you're sitting down here. I got some bad news for you. It turns out there was a sea breeze circulation, an onshore flow on both shores of the bay as the sailboats were going up the bay. And what happened was our sensors were at the surface, and they were showing an onshore flow on both shores. So we thought the boats thought they'd try to ride that wind up the shore. Well, it turns out the bay breeze circulation was so shallow that the wind was onshore at the base of the mast of the sailboats, but offshore at the top of the mast of the sailboats. So the net result was that didn't help them at all. But I just wanted to let you know about the three-dimensional aspect of sea breeze circulations. Cold front comes through, winds are maybe the same at all levels from the same direction, but the three-dimensionality of wind is really difficult. And Bill was mentioning about using airports and things like that. For a long time, all we had was 10-meter winds. surface winds. But basically, we need to know a lot about what's going on in the lower boundary layer, and we really don't know a lot about what's going on right now. So I'd be curious from a development side, when a farm doesn't produce like we thought it did, it might be interesting to try to back out and try to see, what did we not account for meteorologically and try to learn from that, so maybe we could do more advanced assessments in the future. So just a little bit of thought that I thought I'd bring in. Now it's your turn.
Great, that was a good setup. Okay, yeah. Well, I am first of all, I have not been in this business very long. I started off as actually a theoretical physicist and did some work in the stratosphere at NASA in stratospheric dynamics, and then I moved below, as my friend calls it, the fundopause, and then finally getting into weather and ultimately the black hole that is boundary layer. And so these things I'm going to show you today are some things I've picked up along the way. I've just really started modeling and looking under the hood. And so this is some of my adventures in looking at measurements and models, comparing them, and some of the things I've found. So this is, I put plus friends here. Dan Ancona's up there, he's a friend. Various students and colleagues have discussed things with. So first of all, the regional meteorological features that drive the wind in the mid-Atlantic are very complex. One is the physiography with the coast, the highlands, the bay. Global synoptic, mesoscale, local circulations, as Jay was just saying. The terrain is just very complicated. Then we have the large-scale climatology, the Bermuda High. We have certain phenomena that occur because of the Appalachians, like cold air damming. That leads to low-level jets. The mountains, cooling of the mountains leads to low-level jets. I'll show you a simulation later. Extratropical transitions of tropical cyclones, nor'easters, lots of stuff. One of the reasons for the synoptics is the subtropical jet stream. Now you probably hear in winter, they say the jet stream is dipping down and it brings us cold Arctic air. Well, we have a subtropical jet also due to the overall global circulation, and that impacts the weather along the mid-Atlantic East Coast as well. I'm going to show you just some different observations, in situ. By that I mean at one point, remote from microwave profilers, some towers, balloon data. I was going to show some satellite, but this talk got too long, so I have to drop that. And so I'm going to also show you some results from EWIT's Eastern Wind Integration and Transmission Study. They did a simulation. Going to take a look at that, compare it with some data, and then show you a few slides from my low-level jet simulation. As I said, scales of variability. The atmosphere is multi-scale, and the surface is multi-scale, especially in this part of the country. Typically, when we use the term mesoscale, we're talking about a few kilometers to, I guess I can't. Can I point with this? No, I guess not. Okay. Synoptic, mesoscale, few kilometers to about 100. There are local sea breeze, as Jerry was just saying, and in the mid-Atlantic anyway, we have these very sharp gradients in surface roughness, land type vegetation, land sea thermal contrasts, you name it. This picture just shows, really couldn't find much here. It's just a sense of the overall circulation. We have this high pressure system here called the subtropical high, Azores high, Bermuda high. It's a high pressure system that is due to the overall global circulation. That impacts our weather a lot here. On the other hand, we have all of these different land surface types. The boundary layer, roughly, we'll say it's 1 kilometer, but it can range from 100 to 1 kilometer, and this is where all the action takes place for wind. The turbulence is a problem. We don't worry about turbulence up in the free atmosphere, but where the part of the atmosphere that's coupled to the land surface is pretty turbulent, and models have a problem with that. So this shows, I pulled this off the web last night. This just shows the turbine and a little bit about the wind profile in neutral, unstable, and stable conditions. On convective conditions, this is middle of the day, there's a lot of turbulent mixing, the surface is warm, you have a lot of turbulence, and that mixes the wind profile. It mixes the momentum. So you tend to have sort of a little dependence of the wind on height. In the stable boundary layer, on the other hand, when the surface has cooled, the surface can, we say, frictionally decouple from the wind, which means that the lack of turbulence is, the upper level wind is free to flow. It's not dragged by the surface. The thing that couples the wind to the surface is the turbulence and the turbulent drag. So you tend to have, as a result, you tend to have stronger winds at night. Now, this is what Jay was just talking about. For the old Star Trek fans in the audience, the trouble with Tibbles. This is a thermal internal boundary layer. I got this out of Stull, the sort of Bible for boundary layer meteorology. What happens when you have or rapid changes in either the thermal properties of the surface, like, for example, land, water, or surface roughness, is you can have boundary layers within boundary layers. And so that can cause the wind to vary with height in a way that can be very complex. And the other figure to the right shows that the sea breeze circulation, which Jay was talking about. As far as measurements are concerned, the existing measurements, in my mind, are a real challenge for wind resource assessment. The tall towers are great. They really are sort of a ground truth, but they're just very sparse. Some people extrapolate from the surface from 10 to 100 meters. From what I just said, that is clear that that could be a real problem. I don't think, at least I'm looking at this, but I don't really know what is known quantitatively about statistical symmetries, which is to say, to what extent do the wind probability distributions depend on direction, if I move north, south, east, west, location, just displacement, and then isotropy. Well, we know that isotropy is direction. Stationarity is invariance in time. Now, we know that the wind is changing. There's diurnal and seasonal variability, as I'll show you later. But overall, I don't think that the statistical symmetries have really been quantified that well. Some of the measurements that I'm going to show you now are from some fortunate tall towers that Dan Ancona and I have the data, and I am looking for more. At the top, Aberdeen Proving Ground, Beltsville, Howard University Research Center, they have a wind profiler. Sterling, this is a National Weather Service. Wallops Island, I have some anemometer measurements, very high resolution from there. Eastville, Eastville, I have Crisfield too, which I don't have on here. I'm going to put it on here. It's right here. Crisfield location. Newport News. I don't think I'm going to talk about all of these, but it's just that the variability throughout this region is really is apparent when you start to compare these. So for Aberdeen, I had high-resolution radiosondes. So that's a balloon. You send it up, and it takes a profile. And so from these balloons, we can get at least a sense of how the wind is changing with height. And this figure shows you the seasonal variability of that. Much stronger wind shear in the cool season, weaker wind shear in the warm season. The problems with using balloons and radiosondes, even though it's a fantastic database to use because it's multi-decadal, but of course the balloon isn't really taking a profile. And so I am now worrying about what a statistical evaluation of the wind over many decades with the radiosondes, what that means. The Wallops Tower had 6 anemometers on it, and what you can see here is how the wind speed changes with height. It's very nearly linear. This was from August 09 to March 10. That's all I had. Maybe logarithmic with a exponent very close to 1, but it is very rapidly increasing with height. There is Wallops Island. If we look at a probability distribution of the wind shear, which is the wind at 91 minus 51 meters, so kind of across the rotor. The probability distribution is, the wind speed difference. This is 2 meters per second 4. There is a tail in the cool season where the difference in wind, say probably maybe 5, 6, 7% of the distribution, you have wind shears greater than 4 meters per second across that 50 meters. So I've done this analysis for some of the other towers. This is a probability distribution below of the wind shear exponent, and I'm just fitting it to a log. I'm not saying the wind is logarithmic, I'm just fitting it. And wind exponents from that are 0.4-ish. Other locations, the wind on the right, Newport News, there the wind doesn't nearly change as rapidly with height. Not sure why. This is just probability distributions of the wind at 91 meters and the wind at 46 meters. So, and you can see for different seasons, they are there's a lot of wind shear. There are also some of these distributions are sort of multimodal, and so I have to look into the reasons for that. There's some different wind regimes going on. This is just a chunk of the data where I'm just plotting as a function of time the wind speed, 91 meters and 31 meters. And you can see how great the differences can get. And over a period of a few hours, you can have differences here of 4 meters per second. So this is the instantaneous wind shear we're looking at here. It's for this particular time. Okay. Okay, so that's wind shear. This is just Crisfield, which is the location that I don't have on here. This is the widest, well, nearly the widest part of the bay, and so we have a very, we have a wide open water fetch. And so we might expect the wind to accelerate over the bay, and we might expect the wind to be very high at that location. And so these are the probability distributions, but I'm going to show you some of the seasonal variability later. In the cool season, there are kind of a bimodal distribution, but wind speeds greater than 10 are really very common there at 76 meters. The warm season distribution, you know, when that's May through October. Those months behave statistically the same. The cool season, November to April, they behave statistically the same. So that's why I grouped those into warm and cool season. Some of the other tall tower multi-level anemometers, there's others, one's in Ohio, Bratton and Wommeldorf, and I'm just showing this. This is in Ohio, Athens, Ohio. There was a terrain, the elevated terrain approaching the mountains from the west, and the wind shears that she finds on that how many anemometers? 1, 2, 3, 4, 6 anemometers up to 240 meters, and the wind shear is very high here, and it weakens in the middle of the day. The wind shear is weaker because you have turbulent mixing. The wind shear exponents, the graph on the right, early day, early morning, late night, 0.5, 0.6, 0.7. Okay, now I want to, am I okay with time? Okay. Now I want to show you one of our favorite data sources, which is the Chesapeake Light Tower anemometer. It's at 43 meters. Right there. At the entrance to the bay. I have chosen to do this, I'm looking here at the seasonal and diurnal variability, local time. I have taken, and because I didn't want to bias any of these plots with missing data, I have chosen 3 segments of years, and I have eliminated any years with missing data. So the first plot shows, and each of these includes many years, I mean maybe 5, 6. The first is 1986 to 1995, and so here we have the Chesapeake Light. We have our weak period that occurs in midsummer, as we all know, middle of the day, midsummer. Winds pick up after 8 p.m. Again, that's a nocturnal winds picking up. We have strong winds, of course, in the winter. A somewhat weaker period, and the time of day of that weak period, that depends on the month. So the transitional months are April and October. As we go to the next decade, 1998 to 2009, the distribution of wind, the patterns of variability begin to change a little bit. In particular, the winter winds seem to be are stronger during this time. And finally, if we go down to 2004 to 2009, there's only 1 year missing there, which is during the Katrina period. You can see that the winds really do seem to be increasing. I don't really know why this is, and I am trying to figure this out. You have to be extremely careful when you talk about trends. The meteorologists go all over you, for one thing, and you have to make very sure that there were no instrumentation changes or other things happening. So it appears from this plot, which shows the average wind as a function of season. This is wind speed. And so it would appear from this that there is some increase in the wind from 1985 to 2010, but I'm not sure. I have tried to correlate this with certain climate indices, and I wasn't successful. But a new paper has come out that says that the subtropical high which may be controlling this, seems to be moving westward and strengthening. So I don't know. Could be climate, it could be just some natural cycle. I don't know. So as far as models, I'll show you now some results from the Eastern Wind Integration Transmission Study. This was a model. They did 3 years, 1 kilometer resolution, 80 and 100 meter height. I'm not going to go through all the details here. I have 1 kilometer. Actually, it's 2 kilometer grid. And I'm not going to give you the details for those of you who are interested in the details. We can talk later. But basically, their model was a mesoscale model. And they also used the WRF, the sort of state-of-the-art weather research forecast model. That's also what I used for some of my simulations that I'll show you. The simulations that I'll show you of the low-level jet on August 3rd, 2007. So here is a model. Let me just say a few things about models. When you run a model, you want to run it at very high resolution. But you can't do that because it's computationally too intense. So what you do is, first of all, you have a global circulation model that provides the very large-scale boundary conditions, and then you have nests, as they're called, of higher and higher resolution that are embedded in one another. So for each nest, the lower resolution nest provides the initial and the boundary conditions. And in my simulation, the lowest nest there has 1 kilometer resolution. The outer nest is 27 kilometer resolution. So if we look at this idea of modeling, and this really gets into some of the issues with wind resource assessment in my mind. You have to have a good global climate model on the boundary. Okay, what do global climate models have to do? They have to represent a wide range of physical processes, and the most difficult ones are the way that the surface couples to the atmosphere. You have a number of, you have surface runoff, you have fluxes of moisture and heat between the soil and the atmosphere. I mean, the way in which the surface communicates with the atmosphere, this drives the wind. So you have to get that right, and it's extremely complicated. I'm just showing down here a little part of this piece, which is a little plant in the root system, and the way that a root system is going to take water up from the soil is going to be important, because the way that works will determine what the soil moisture is, and what the soil moisture is going to determine what the thermal inertia is, and what the thermal inertia is going to determine how rapidly the surface warms and cools as time of day, and that controls the wind. So this little plant, and you can imagine all of the other processes that go on, is a complexity that is disturbing. Okay, this is just making the same point again. When you're over water, now you have to worry about coupling to the ocean, the waves, and so forth, which is another whole ball game. The GCM has to get the large scale right. So what the GCM has to do is it has to get this, here's this subtropical high pressure system, for example. And this is Hurricane Wilma that was steered toward the Yucatan by the subtropical high on October 20th, 2005. The westward expansion of this subtropical high really steered the storm to hit here. If this system had been, maybe further north, a little weaker maybe, this storm, which they originate from the East African coast, easterly waves, this storm would have come and maybe hit us. And sometimes they do hit the coast. And a lot of that, not all of it, but a lot of it does depend on where this climate feature is located. Well, okay, I'm going to go through this very briefly. This is just another thing that those large models have to get right, and that is the large-scale, upper-level placement of the jet stream. The placement of the jet stream was crucial for the extratropical transition of Hurricane Gaston in 2004. When the storm came on land, it re-intensified because it interacted with an upper-level front. And some of the wind speeds in it the gusts were up to 82 miles an hour. This just shows the meteorology. The models have to get the small scales right, not only for sighting purposes for wind, but I'm doing some air quality modeling now too. And here is a very interesting story. This Edgewood, Maryland, is right there. Now, Edgewood has some of the highest ozone exceedances around. It has very high ozone outbreaks, and it's sort of unique in that respect. And one of the issues there is the sea breeze circulation and the complexity. There is some convergence or something happening. And what it does is it sort of focuses the winds, and then it sort of recirculates the ozone. And the only way that that could be seen is going to really very high resolution. That kind of thing does not show up in a regular mesoscale model. The EWITS study was, okay, so now that's what models have to do. So now we go to the EWITS study, which was these are all the locations I'm showing here are the ones in the mid-Atlantic. The study is a mesoscale model. It was 1 kilometer, and it did a 3-year, every 10-minute wind simulation. I have the data at 80 and 100 meters. Now, what I did is I just took a subset of these locations. I just went, the ones on the left are numbered from like 1 to 8 were locations along the ridgeline. And then 9 to 16 were along the coasts, and then the rest 10 to 25, that was offshore. The variability in the wind power, these plots show the wind power density versus hour of day for different months. The blue are all of the offshore locations together. The mountains or the ridge line is the red, and then the bays and sounds are the others. So this shows, this is for the 2004, this is for the entire year. This shows hour of day and the wind power density. And you can see there's just a tremendous variability across the region in terms of the wind power density as a function of time. Now, I chose wind power density because you can add it. You can't add wind speeds and cube them, as we all know. So when you sort of average them all together, you get a much smoother, more constant supply of energy, which is really one of the points of this study. The midday warm season minimum does not go away when you average. You can't compensate for that. You can't use mountains and offshore to get rid of that. I'm not going to, this is just some point-to-point correlations I did to look at the correlations, but I don't want to go past that. These are plots of the coastal, the mountain, and the offshore sites. And these are plots that show, again, these are contour plots of wind speed, season on the vertical axis, and time of day, local, on the x-axis. The point here is just to show some interannual variability in the seasonality and diurnal variations in the wind. And they do vary in some places more than others. In the offshore sites, there is a pretty substantial deviation, more than maybe we would have expected. Overall, I think you can see the colors here. The orange is 7 to 8 meters per second. The light green is 10. The blue-ish is 5 meters per second. So you get this 5-ish meter per second midday warm season kill-off of the wind everywhere. Oh, well, let me see. What do I need? Dan Ancona and I just did a study of the barriers to wind, and so I just looked at several locations comparing EWITs to the closest location where where I had data. One thing you can see from this, first of all, these are the EWITS studies for 2004. These are the tall tower data that I had available for the study. They are not the same year, which is too bad. But I used some of the buoy data to look at the interannual variability and convinced myself that it wasn't the issue here. These two bottom ones just show for these 2 years combined, the EWITS study and the Chesapeake Light. Now Chesapeake Light is 43 meters, this is at 80 meters. But having said that, there is no way that you can logarithmically scale Chesapeake Light up to 80 and have it be the same as 80 meters per second, because the diurnal variability, particularly in the transition seasons, is just very, very different. EWITS has a very large wind late afternoon in the transition season that gives 1,000 watts per meter squared for wind. And we don't see that in the data. Oh, so some more comparisons of EWITS with light tower. I scaled it up a little bit. It's not too bad. Overall, it's higher. Of course, it's at a higher, the EWITS study is at 80, Chesapeake Bay's at 43. Okay, expect it to be a little higher. It doesn't look too bad, but it doesn't seem to be able to reproduce the diurnal and seasonal variability. I tried different exponents just for kicks, and well, that's on the right side. Well, I have done many of these studies. Some of them look okay, some of them look bad, and I think, let me just show you one more, which is what we all kind of like to see. We like to see a time series, even though we know that's a very, very harsh test for any model. But here it is, EWITS and Chesapeake Light, and here it really doesn't look so bad, this early January period. What EWITS is able to capture is the weather systems, the synoptic variability. The smaller scale fluctuations, couple of meters per second maybe, it doesn't always get those, sometimes it does. The plot on the very bottom is first couple of weeks of August, and EWITS is overestimating the wind by 2 or 3 meters per second during this time. Probably running out of time. Just want to say one more I'll make this brief. One more thing about the Mid-Atlantic is a phenomenon called low-level jet. These are low-level winds in the lowest few hundred meters of the atmosphere. They come from, there's various forcing mechanisms, but one of them is the cooling of the Appalachian Mountains. And so what that does is it creates a temperature gradient at a couple hundred meters above the surface, and that temperature gradient drives a jet. And then that jet is rotated to a southerly direction by the Coriolis force. So that is not the only way you can get jets. You can get jets from cold air damming. You can get jets from upper level jet streaks and all kinds of things. This is the mechanism. Thermal wind relationship, for those who know that. For those who don't, I'm just going to keep going on. So here's a picture of the wind speed, regional wind speed using a 27 kilometer model. So the white contour is the 300 meter topographic contour. And you can see the jet. Now, this is at 312 meters because that's roughly where the maximum was. You can see how this jet, you can see how it is definitely correlated with the topography. It extends, it's strongest really in the Maryland, the coastal plains. It goes off to the northeast, and it can impact the offshore winds, maybe in Delaware. I haven't seen it play a big role in Maryland and Virginia. I do know there's Carolina jets. I don't know too much about them, but anyway, this is what this jet looks like. This jet sort of came to my attention from the air quality people because air quality, they noticed that there were ozone exceedances during the times when these jets occurred. And what the hypothesis is that these jets are bringing a lot of pollution into the mid-Atlantic. And when the boundary layer, when convective turbulence brings this stuff down from aloft, the ozone rises. And so this is sort of, I think, where people, at least in the mid-Atlantic, became interested in this. Now, this Southern Great Plains jet, low-level jets happen all over the world, but I think that's the interest in it. Now, it happens. I don't know about the climatology. I'm working on that. But it's not a rare occurrence at all in the summertime. Just to say one more thing about resource evaluation, this is the point that I want to make here. If you look across the jet, I can find a Sterling and I can find 2 weather station data across the jet. And what I would be looking for here is I would be looking for the way the nighttime mountains are cooling. A few hundred meters above the surface, the temperature's not changing. It's changing close to the surface. I'm looking for a change. I'm looking for a cooling in the elevated region because that's what's driving this. So I compared my results with some radiosondes, and what you can see here is the location, which is to the northwest. This is the radiosonde is really cooling rapidly. The model. This is this is Wallops. This is east. This is west. So what you have is you have the Sterling. The elevated region is warmer. Near the ocean is cooler. That reverses at night. And that reversal is what drives this jet. So the point here is that when you're evaluating the wind resource, there's a lot of other things you have to look at. I mean, you can certainly just take the model output and you could say, oh yeah, it gets this, it looks okay. But you should also have to look at all the other meteorology and make sure that you're getting the right answer for the right reason. So that involves a lot of other analysis. I know, I'm running out of time. This just shows wind profiles. Wind speed is a function of height for the model compared to the profiler, and the observations are in black. So we can get this with the model to different degrees. I'm not going to show that, not going to show that. So, Mid-Atlantic's complex. Challenges for wind resource evaluation come from both the modeling and the measurement side. Anemometers, too sparse, really. Multi-instrumented are good because at least they give us some idea about what the wind profile is. We need more vertical profiles. That's the upshot. Models still do have a way to go. The land surface radiation turbulence schemes, they're not quite where they should be. Is higher resolution the answer? Sometimes yes and sometimes no. I found not a whole lot of difference when I went from 9 to 1 kilometer in a lot of these jet simulations, so I'm not sure. I guess, I'm sorry I took so long, but anyway, that would be it.
I can tell you folks that as a meteorologist, that was pure gold. I mean, basically what she told us, there was a lot of charts, a lot of complexities, but you know, the wind energy is the wind speed cubed. And so, you know, learning a lot more about the wind and where these nuances lie are huge. I forecasted wind for windsurfers, and so for many years, and this is a different crowd, but the name of the game was the same. They want a lot of wind because they can go fast on their sailboards. We want a lot of wind because we can turn that into energy. And one of the things like this low-level jet, a low-level jet, that's gold. I mean, that's good stuff. And basically on the Chesapeake Bay, just as Fred's coming up, basically we'll get these low-level jets. We had the sailors there say, can you keep your weather stations up all night long? And we're like, why? And they're like, well, basically at 5 o'clock in the morning, the winds are blowing 25 knots on the days like this where it's hot and humid. There's no wind in the middle of the night in D.C. or Fredericksburg or Richmond. Over the Chesapeake Bay, the wind will come up about to 20 knots out of nowhere around midnight and blow solid until about 7 or 8 in the morning. And the windsurfers love that. And so, you know, and when I went out to Tangier Island to locate a weather site, the guy on the ferry goes, you mean you guys didn't know that? The crabbers get beat to hell every night when they come out here in the winds. And so, you know, this stuff's going on. And basically when it comes to wind energy, this is valuable information that really can be of a lot of use for wind energy development. Lynn just gave, I mean, it was just, that was kind of like my whole undergraduate class load in half an hour. But it was so good, and it encompassed everything from, you know, seasonality. I mean, like when some windsurfers say, when I was a kid, it was much more windy. Well, La Nina and El Nino, there are actually decades where winds are stronger than they other times. That's a big deal when it comes to resource assessment. Maybe your 1 year of data that you took happened to be a relatively low wind yield year, and something like that. So the wind variability decadal is a lot. Seasonally, it's a lot. I told you about the sea breeze circulation with the sailboat. So there's so many degrees of variability. I think you did an excellent job of showing just how complex things are. And I think it may seem over these guys' heads to understand all the meteorology, but it's really important when it comes to wind energy development. I thought you did a marvelous job of showing the complexity of what was going on. So Fred, we're going to shift gears a little bit. Fred, basically, we need new gizmos. As Lynn said, we need to understand the boundary layer. We have 10-meter winds. We need to find more creative and effective ways of getting the lower boundary layer winds because the variability is so good. And his company has developed some real neat technology, and he's going to enlighten us as the last speaker of this panel to tell us a little bit more.
Good. Thanks, Jay. And I recognize my position between you and lunch, so I understand that completely. But as Jay said, my name is Fred Belen. I work for a company called Catch the Wind. We're located in Chantilly, Virginia. We're one of the companies that does wind energy work here within the state. And so I'm very glad to be here and be part of this panel. We make wind sensors. More precisely, our primary product is working with improving wind turbine controls and wind turbine performance. But the sensors have many uses, and wind resource assessment clearly is one of those. So I'm going to talk a little bit about that. We tend to talk about our systems as being optical sensors. The wind industry likes to talk about it as LiDAR. So it's no mystery or magic here. For those of you that are familiar with the term LiDAR, that's really what we're talking about here. Although there are many different ways to do LiDAR in the these various sensors. I think Lynn really hit a lot of this, as did Bill, how important data is in this particular world. I remember the old movie, It's a Mad, 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 Mad World. I think in the wind energy business, it's a data world. That in fact, while models are great and CFD is great, all of the people, the modelers, the wind performance people, the people who are doing wind resource assessment, they want data. They want data to design wind turbines. They want data to find out where there's a good quality wind resource. They want data to be able to design a project. They want data to get financing. They want data to get permits. They want data to be able to assess the performance of a farm or the performance of a turbine. They want data to run the control system in the turbine. And they will want data to actually be able to project near-term forecasting for ramps coming and going out of a wind farm. So it's data. And in my little 15 or 20 minutes of glory here, I'm going to talk about a pragmatic answer to fill in a big gap we have in the data that Lynn talked about. We need more wind profiles. There's not enough anemometers. There's not enough towers. You can't fill in the gaps vertically or horizontally to get the data that you need. And our company has been working with a partner, Axis Technologies, that has been making meteorological buoys for decades, and adding to that buoy the capability to put a profile up above the water surface for offshore. This being a Virginia wind conference, symposium, we all probably know how important offshore resource is for this state and for the Central Atlantic states in general. And so this is a particular niche, and I hope that you'll find some of the things I'm going to talk about as being helpful to understand where technology, as Jason's saying, can take and help fill in some of these gaps. Just a moment about what our company does. Again, we really do wind turbine controls, and we use backscattered light off of a laser to talk to the control system, to do a whole series of things that can improve turbine performance. Jay mentioned the overarching wind energy problem of underperformance. Some of it may be in the accuracy of the projections of the wind resource assessments ahead of time, but some of it's also in the inefficiency of the turbine operation itself once in operation, because most of the turbines are using wind data that comes off the wake in the back of the nacelle that compromises and delays the response to the control system. So using lasers helps the efficiency, and you can pick up half of what you lost in your performance just by improving controls. But this same sensor that we're putting on top of turbines has other applications, and that's really what I'm going to talk about today. In terms of topics, I'm going to talk about some trends in offshore wind resource assessment, particularly as it drives the sensor world. If you're a hammer, the world looks like a nail. If you're a sensor guy, everything looks like wind profiles. So I'll talk about that. Remote measurement using optical sensors, and then our field experience with both trials and commercial deployments of these kind of sensors, how it's working and how this is actually answering some of the key questions of, are these sensors accurate enough? Are the buoys persistent enough? Can they handle this harsh environment? Is this a practical answer to fill in some of the data? Basically, offshore, traditional methods are going wanting. We can't put up Met towers where we want them. Very, very expensive. Once you put them up, you can't move them. Buoys have their own set of issues, but they're much less expensive. They're very mobile, and they combine with the wind resource, other things that can be measured, such as currents, wave heights, salinity, and other kinds of meteorological data that can be immediately correlated to the wind profile. So they have some amazing abilities to fill in a data gap that we have right now for offshore. That's what an offshore Met tower looks like. There are some around the world. There's never enough, and they're very expensive and to permit and to build. This is what a typical buoy looks like. This buoy happens to be one of several that's being introduced into the industry now that includes a vertical profiler. This is called a Wind Sentinel. This is a particular product of Axis, the partner we use. And you'll see that it has lots of different things on there, everything from its own energy production engine to handle all the hotel loads, both by solar and wind generation. It actually even has an internal gas generator or diesel generator to carry you through long dark periods or slack periods in the wind. Based on recent deployment in Lake Michigan, it looks like one load of fuel on this buoy will basically extend the service period to about a year. So this thing will run itself for about a year. It has its own data logger and can be equipped with satellite rebroadcasting as well as data storage capability. It's about 4 meters, 5 meters, something like that. It's not real big, but it's pretty robust. The advantage of this particular buoy or any of these buoys that have vertical profilers should be pretty obvious. They're lower cost, of course, than putting up a tower, as I mentioned. But this buoy here was originally called a Nomad. It's been around for a long time. It's got a hull shape so that it's moored by a bridle and can handle some pretty substantial waves and very harsh environments. And it includes its own, as I said, its own data controller that has a couple decades of experience behind it. We can moor these things out to about 400 meters, which means the continental shelf is well within range. And it's designed to handle long swells on the ocean. We actually experienced some very severe, shorter waves in Lake Michigan this last fall, where we were getting 8-9 meter waves, but they were very, very sharp, and they were actually harder for the buoy to handle than even the long swells are in the ocean. But of course, by putting the optical sensor on it, you've now basically got a Met tower type performance out in the ocean quite a ways from shore. That's the sensor. It's about the size of a watermelon. It's all fiber optics inside. There are no moving parts, except for the stupid windshield wiper. It's built to military standards and tested to that standard because that's where it came from. It was originally designed for an aircraft flight control sensor. As I said, it's in a sealed enclosure, sealed and purged. And because of the fact that with the way we do our LiDAR, I want to use that term, we actually have fixed beams that are pulsed simultaneously. There's various ways to do backscatter LiDAR. They all have their advantages and disadvantages. But in this case, where you have 3 beams, they're in fixed geometry to one another, we simultaneously pulse them at 1 kilohertz. So we have very high data rate, and the data that's collected is time coherent. So in other words, it's a time-stamped data instead of sequential data that you get from scanning LiDAR or from sequentially pulsed beams. This data is time coherent so that it can be motion compensated fairly simply through vector transformations and an inertial platform. So this was designed to operate in a moving aircraft. It has a 6 degree of freedom inertial system in it so that it compensates any of the induced wind velocity that would get into the profile measurement from pitch and roll of the buoy. This is a little quick and dirty, but you can see here a stationary unit beside a rocking unit. And although that doesn't look like a lot of rocking, that's about 10 meters a second induced at 120 meters. So when we do our test, you can see from the side-by-side, 1 second data is correlating between the stationary and the moving sensor. We really have a pretty solid answer there. And of course, that's been borne out by a number of our trials. Ashore, all of these LiDARs have to prove that they can correlate to a Met tower, and so everybody's done that. But going out and doing it in the water is a whole different deal. This particular buoy is now currently in part of 2 different commercial deployments, but back before that there was a very extensive trial done in Vancouver, British Columbia. That trial took place in '09. We had a stationary Met tower and a stationary LiDAR on a point of land, and then 700 meters out into the seaway, we had a buoy that was there for an extended period of time, and they did, I guess we had 3 different heights that were compared between the sensors, and then those data were analyzed by 2 different third parties. The first was Grand Valley State University, which was part of a Michigan wind energy consortium, which I'll talk about in a minute. And they were able to confirm from the 2 sensor data sets that in fact there was no operational significance difference between the profile moving and the profile standing still, that in fact the motion compensation was doing exactly what we said it was going to do. It was also then analyzed by Gimmerscher-Lloyd Garada-San. They came up to the same conclusion using a 2% difference criteria. It easily stayed within a 2% criteria throughout the speed range and the vertical profile range. We've been selected last year to be part of this particular deployment. This was a two-phase deployment. The first phase, we were inside Lake Muskegon. That's on the west coast of Michigan. And during that period of time, we operated from the lake, which was fairly benign from a rock and roll standpoint, but it was close to several Met towers. We did a lot of correlation testing against the Met towers, fully calibrated, checked out throughout the range that they had. But as you can imagine, the Met tower wasn't the full profile height, and I'll show you some comparisons in a minute. And then after that calibration phase, it was moved out to 4 miles into the main lake itself, which we could correlate to some extent with NOAA and other Met tower that was here at the mouth of the Muskegon Lake. Some of the results of that have opened up a trove of data for a number of users in the Great Lakes region. Here's just an example of kind of what this kind of a profiler can do for you. Your Met tower can get up to a certain height, and then your optical sensor can fill in the data above that. The issues, of course, that you face if you don't have a profiler that goes to adequate heights, and if you're looking at an offshore turbine, it's going to need data up at 120, 150, or even 200 meters up. Your Met tower isn't going to do that. And if you take data such as in this plot on the right, which is a storm, you'll see that you extrapolate your Met tower data, you're going to be way off from what the actual profile is. So if things are all nicely behaved, you can extrapolate your Met tower. But if they're not well behaved, you need data. And in fact, they found there were a lot of instances where the optical, the laser data was giving them information of the upper boundary layer that they had never seen before. Here's an example of what was being put on the internet during this deployment. These are time histories of various sensors. Some of these range gates or these gates are off of the buoy. Some are from nearby Met towers, nearby being four miles away. But you'll see the kind of correlation we were getting over time. We were in this deployment for 2 solid months, 100% sensor operation, never had a failure of the sensor. We brought the sensor back in and we put it on the pier during the ice period of the winter, and it continued to give data all winter. And that was speed. This is direction. Those kind of ugly spots are wraps where it goes up 360-degree around. But the wind direction correlated perfectly. The wind speed correlated quite well as well. And now we also use this to correlate models. These are models from the Great Lakes Coastal Forecasting System, and they'd never had an ability to do any upper boundary layer correlations with their models. And you can see this is remarkable correlation really for that kind of a model that they're getting with the buoy data. They also were able to study the incidences of storms across the lakes. They'd only had 10-meter data out in the water. Now we were able to give them 140-meter data, and they were able to see the kinetic energy that was coming in during the storms at the upper heights that they had never seen before. And now they're working on a revision of their storm models and how they can predict and ramp storms on the Great Lakes. Their conclusions after first phase of this is over, they had some tremendous data, particularly about the turbulence and the upper height kinetic energy. Of course, it's helping the modeling people, the weather people, and the prediction people that are looking for wind resources for turbine installations in the Great Lakes. We're now into the second phase of this deployment. Our buoy is out in 45 miles out into the lakes and has been performing ever since early spring. Again, getting very, very high percentages of data availability across a range of weather conditions. Then an additional commercial deployment that's underway right now is Fisherman's Energy. I don't know how many of you are familiar with that. That's what's going on off of the Jersey shore. We had our sensor onshore at Cape May for an 8-month straight assessment ashore, operated at 98%. Then we put it on a buoy. That buoy's been about 10 miles off Atlantic City, taking data now ever since January, February timeframe. And we're going to bring it in close to shore in July and do a correlation test against a wind cube, which is another vertical profiling LiDAR that's out on the steel pier. It'll be stationary, the buoy will be in the seaway, and the Lockheed Martin wind tracer will be on top of one of the hotels to give a view out over the ocean as well, to see what kind of correlation we can get between these various sensors. So in summary, I think we're coming of age here. The accuracy and the ruggedness of this kind of an optical sensor on a buoy is being proven. We're now into 2 different commercial deployments. There's a number of these products coming into the marketplace. We believe our product has some technical edge because of its motion compensation in this particular application, but it certainly is providing new data, especially for the offshore customer. Data that's filling in gaps that Lynn was pointing to as well, that we just don't have the Met Tower. Met Towers like that are of the height that you need for offshore turbines are tens of millions of dollars to install. And so this provides a way, a practical, pragmatic way to fill in some of those data sets using buoys and at a lower cost, and be able to move them around in a wind campaign and fill in data both spatially and horizontally and vertically. So that's kind of my spiel, and I guess we'll have a general question and answer before your lunch.
Thanks, Fred. When you were rocking that your instrument back and forth, I was starting to think about Humpty Dumpty. It kind of looked like had a great fall there or whatever. But the sailing anecdote I have on this one is that basically last New Year's Day there was a frostbite regatta, and basically down in the Norfolk area, and the sailboats are sitting on this glassy water, and they're not moving. And so I go across the tunnel, and there's a flag pole over at Willoughby Spit, if any of you are familiar with the Norfolk area. It's quite elevated. The flag is just whipping. I mean, it's just blowing. It's just really blowing. So somewhere between the top of that flagpole and the water surface, the winds went from 25 knots to nothing. And so imagine that across a turbine, you know, somewhere halfway across the blade, it's calm, and then halfway up the blade, it goes from near 0 to 25 knots. So that's the type of thing that Fred's instrument will be able to really find, is that what happens is the water's cold, very stable. This was a warm southwesterly wind day. The warm air just could not scour out that colder air, and it provided a dam. So that's the type of thing that instrument would be very useful to help undermine. So I think we got a good wide array of descriptions, and Bill started us out with a good primer, the basic what wind resource assessment's all about. Lynn gave an excellent meteorological overview, and I'm just amazed at how much you crammed in there, because that's so important. That basically the one extreme to the other, and then Fred's description of how modern technology is helping out the problem, I think, was an excellent compliment. And so at this point, I guess I don't know if I'll do my best, Jerry Springer, to come up and hand the microphone to somebody, since we haven't written down questions. But if anybody has questions, is it too late to write down with the time? Oh, great. Okay, then let me get some cards. You want to get them from that side, or okay? I guess if you don't, do you want to answer your question to the mic? And I'll take it down for them to answer.
Yeah, I'm interested, given the excellent list of challenges that you've put before us. What are the Europeans doing with all their offshore work to try to solve and overcome these issues in their expression of, you know, from, I guess, Ireland over into the North Sea? There's quite a lot of construction going on. And it would seem that they must have some more confidence about where to put these devices.
That's an excellent question. And as I'm walking down, I know that I have heard some anecdotal stories about how some of the wind energy studies there, assessment studies, actually have shown that they didn't do a very good job at the beginning, but now they're learning a lot. And then the other add-on is that they deal with nor'easters, but those storms in the North Sea top out a certain one. But they haven't dealt with hurricanes, so I think that's one area where I will mention that I think we can't learn anything from them. But other than that, I think you're right. In other words, hurricanes will give us a unique barrier that we're going to have a hard time. I mean, if you look at the oil platforms in the Gulf of Mexico, we can withstand 60, 70 knots of wind. But when it gets to be 110, 120, it's kind of scary. So that's something I think we're in Virginia, unfortunately, we'll probably have to deal with that with recurving storms. So do you guys want to give some comments on?
Well, the ECMWF, the European forecasting system at the UK Met Office, is they produce a product, wind forecast, and a data assimilation product where they blend measurements with the wind, and it is top notch. It really is much better than a lot of stuff that we have. I have a colleague who works on satellite retrievals, and that's what he uses all the time to compare with the satellite. It's proprietary. You have to pay for it, which is really too bad. So I don't know what they do in detail with their boundary layer scheme. I've never really looked into it. I think I probably should, though.
Either of you have comments on that?
In Europe, particularly in North Sea and north of the British Isles, they have a number of platforms out in the water. And all of our European colleagues utilize those platforms to be able to place sensors out into the ocean and fill in some of the data that way. So vertical profiling is being done by the Europeans. They actually started it before we did. And if they have a stable platform, they have a oil platform or other stable platform, those sensors that they're using seem to work fairly well. They don't have, to date, a lot of experience with buoys, although the Norwegians are getting ready to field one that has a LiDAR type of a device on it. It hasn't really been fielded or been available yet, but they're coming.
I think Lynn was alluding to, there's our satellites also that do offshore winds, and we had a great one called CSCAT, and it went away, and it died. I just learned this week that NCEP, the weather forecasts in the U.S., folks in the U.S. are actually getting access to the Indians' same version of that instrument, so that gives you some stuff over the open water. I think I'll bundle these questions. There's a couple to each of you, I think. So, Fred, somebody had a question. Are you using your instrument at all in the mountains? Yeah.
Yeah, let me make something clear on the profiling business. Axis, as Jay and I talked about ahead of time, Axis is really our wind resource assessment partner. We give them the sensors. They're doing a campaign right now in Canada, in a mountainous area near Maritimes on the west coast, and they have done some others. But the main niche that they've been exploiting, of course, has been this buoy, as you might imagine. We do have, however, wind farms in mountains where we are on turbines. And when we're on a turbine, we not only can give power performance improvement, but we also give them a local wind resource assessment readout with wind statistics, wind roses, distribution of velocity and direction, and a number of other data products which we give the farm owner because of our LiDAR being there.
Just one comment. Fred has actually used some of our Met Towers to test equipment.
Absolutely.
And I must say, even though I guess it's not totally financeable, it's right on. The equipment is incredible. And it also gives you the ability to go up much higher than the 60 meters, which...
Bill, excellent segue, because this is what the other question is. You showed the data going up to 120 meters. What's your upper limit? And the other question is, do you lose any data integrity as you go up to the upper limit?
That's a very good question. Right now, actually, we can operate in most atmospheric conditions up to about 150 to 200 meters. And the reason I had that little caveat there is that all LiDARs are based on a backscatter principle. If you're in very, very clean air for some reason, as we actually have experienced in some of the offshore, where there's not an awful lot at the upper atmosphere, dust particles and pollen, your backscatter coefficient can be very low. And all of these LiDARs are dependent upon backscatter. So we can reliably get 120 to 140 meters in any kind of air. And we usually set a gate higher than that, which may be a little intermittent. So when I talk about 98, 99%, we're talking at the 130, 140 meter height. There's nothing magic here. If we were to increase our output power, we could certainly extend that much higher. We have one unit that Jay's familiar with that has 1,000 meter range. So it's really just a trade space of power and eye safety and PRF, pulse repetition frequency, to determine what you can get. But there is always this caveat that you have to have some backscatterable particles in order to get data. But we're getting very, very high percentages up into the mid 100 meter ranges.
Thanks, Fred. I have two tandems of questions, and then I think we'll wrap it up. I have a couple for you, and then Bill, I'm going to fire this other one to you. For Lynn, it sounds like the question to you is: it sounds like we may be overestimating the wind in the Virginia lease block offshore. How can we get measurements to determine if that's true? And then this is another geographical one, so I'll read this question to you, and you can kind of comment on both. And then when you're done, how would you compare the results of the Virginia-Maryland coastal plain to wind similar areas of North Carolina, where some same projects are being developed? Are you suggesting there will be some unpleasant surprises for those projects? So the coastal plains and then the offshore, about maybe over-promising or whatnot?
Well, the coastal plain has a few meters per second less than offshore. I see this in this EWIT study. Details I can't say because I don't know the specific area that you're talking about, whether there's some local influences there. There seems to be overall, and there was a pretty big bake-off recently with mesoscale models. They overestimate the wind at night. They underestimate it during the day. When they overestimate it during the day, underestimate it at night. And The extent to which that is going to happen is going to depend on the turbulent fluxes. And the extent to which that is going to happen is going to depend on what your surface roughness is, what your thermal contrasts are, all that kind of stuff. So I mean, it's very difficult. Even you need to know whether it rained yesterday in order to understand how your model is working. Because if it rained, the soil will be wet. Soil will be wet, it's not going to radiatively cool. It's not going to radiatively cool, it's not going to drive a flow. So, I mean, I can't say I'm always ready for more data or model outputs, though I love doing this stuff. It's a hobby, I mean. So.
That's excellent, though. I mean, with the precipitation effect on the things, I see that from forecasting that all these different patterns tied together. Bill, the tandem for you are two questions that are kind of tie in the resource assessment from the science perspective to what it means to the wind energy industry. And basically, the first question mentions about the benefits of offshore wind. Is that the afternoon sea breezes are often correspond to the afternoon peaks in energy demand. And basically, the question is that true? And then. And then the follow-up with I was thinking of the nocturnal low-level jet, and maybe you want to expand on this because you see it. I think you see it up in Boston too, where you're a offshore farm you were mentioning to me is these heat wave situations we're in right now. The overnight hours. I mean, I got to believe the energy demand overnight when it's 85 degrees at midnight in Washington D.C. when the low-level jet's cranking out in the bay is probably often also an opportunity to basically take advantage of the resource happening at the exact time when the demand is the greatest.
That is absolutely correct, and that's why. One of the key things a lot of people are looking into is energy storage to capture energy when it's not at peak demand. So I think that balances itself out.
And then this last question is similar to that, but it's basically more of a decadal question. In other words, there's some concern that wind patterns will change with climate change. How are developers dealing with such risks, insurance, and control the allocation of the risk? So.
Again, that goes back to correlating your Met-Tower data with data from airports, data from historical data that goes back through El Niños and El Niños, and I think historical data is key. There's no question about it.
Well, thanks, guys. As you can see, that we're a group that's really obsessed with wind and everything about it, and hopefully the wind energy group can continue to tap the talents and the good work that these folks are doing, because I think it can make a big difference on the success of wind energy. I'm super excited that my career allows me to do something that I think is good for the country and good for society and whatnot with wind energy. And I'm kind of really excited to think that my passion for wind was more selfish windsurfing and sailing related, but I really believe that the same stuff we're learning is very applicable to the wind energy industry, and I think a real necessity if it's going to be successful in the United States. So if anybody has any more questions, speak now or forever hold your peace, or let's go eat some lunch. Thanks. Appreciate it.